Good afternoon, members. My name is Kakuza Michael, and I would like to take you through the model architecture of this project that we are doing. So the model is isolation forest. So it doesn't look for known TB cases, and it finds districts that behave differently, which often signals hidden risks. Because based on the project that we are handling, optimization of resources, our main point is about identification of the areas where we need to stress in for resources and where areas where we need to also stress in for the people who are sick. So this is the diagram as you see it, the model architectural diagram, looking at the 135 districts by the 13 features, which include population, geography, health, access, and so on. So how it works, the model builds 500 random trees, each splitting the data in different ways. Districts that are easier to isolate, those are ones with shorter paths because it is using a decision, it's using trees format. Then we also, those that are treated as unusual, meaning that they have higher TB risks. Also, we set a 20% threshold so that top 20% of the districts are automatically flagged as high risk. This includes the proxy positives, about 42 districts, mainly from the urban or high density areas. So the pipeline flow, data, cleaned and scaled data. Then you have the model which builds the trees and calculates anomaly scores. We have the output that is on the districts ranked by risk. Then you also have the final result that is prioritized the district list delivered via API to support ministry decisions. So to peruse through faster, let us look at the findings. So the performance of the model based on other models that we had done, the 12 models, that is it was the highest on the seven, sorry, on the 7 models, not on the 12 models. On the 7 models, it was the highest. The average precision is there. The security score, the prediction time, 47 milliseconds. Why it won, the Spearman rank correlation that was given to it based on the Uganda TB survey. You can also talk of the no Gaussian distribution assumptions, meaning handles complex multi-dimensional TB risk patterns. And then you come to the district rankings. Here we look at the hidden burden districts, especially those ones which are in high populations. Also look at the rankings. Ranked number 2 in the highest burden, that is the high pop density districts, and so on. So this is the overall rank model. This is the overall score of the model. So the alignments, the model alignment scorecard, isolation forest versus a symbol versus spectral. You picked these 3 models because out of the 7, then you have to pick also the best 3 from the 7. So from the best 3, and it came out as the best model based on the scores that you have seen before. So let us continue to compression model and compression analysis. Why didn't compress it? Because it was very tiny, just 4.2 MBs. Also the speed, 47 milliseconds for the 135 districts. The throughput, that's what 2,826 predictions. Second, more than enough for a batch use. A batch use, that means it's enough for a very big scale because you are trained on 35 districts. Now imagine for the 135 districts. So what to focus on instead? Model monitoring, that is tracking prediction, accuracy, and data drift. Feature engineering. We also have automated retraining pipeline, and so on. So in the conclusions, isolation forest proved it to be the most effective model for TB risk stratification, achieving the highest overall performance, successfully identifies high-risk districts from unlabeled data and addressing gaps in traditional surveillance systems. So when you come to the limitations, unlabeled data, that is true, because some low-risk districts may be misclassified, based even that we consider the few districts, those are 35 out of the 135. Use of proxy labels, abundance based, yes. mostly we looked at the urban regions because the remote areas are a bit technical to find the data needed. So with that on, I'd like to acknowledge our lecturers, Dr. Galiwango Marvin, Harrison.com, where we got our diploma in AI machine learning, Macquarie University, and also our lecturer, Dr. Difference. Thank you for listening to me.
Okay, hello everyone. I'm going to continue from where my colleague Kapoza Michael Owen stopped. Well, I'm going to talk about the problem statement. Let me start with the domain application problem. Our domain, we are looking at latent TB at large, and well, according to studies, according to the surveys at least we took, we came to realize that, there is no actual data that is available to talk about latent TB. There are no statistics, there are no data sets. It is just a minor study that is being conducted as of now, and there is no much emphasis. So honestly, as of now, the government just merely hands over money to different areas to handle such scenario, but it doesn't based on actual statistics. Maybe say that in areas like Karamoja, there are very many cases of latent TB. It doesn't have such statistics, so it just randomly gives out money. And well, that's our domain application problem mostly. Well, when it comes to the computational problem, like I said, there is no recent LTBI survey that was found. We didn't find anything, and even in the data gaps for the available data that is already existing, it has gaps. It's outdated, and it really cause mostly what we're basing on. We're basing on PDFs. We're extracting data from PDFs. Not there is no actual legit database that actually existed. Something that we had to come up with. Moving on. One of the research questions and objectives we asked ourselves, what is the current prevalence of LTBI in Uganda population? Its key subgroups. What host behavior and environmental factors predict progression from LTBI to active TB in Ugandan populations? Are there geographic hotspots of latent TB infections or TB incidence in Uganda that should be prioritized over intervention? And then can predictive risk analysis be developed to identify which individuals with LTBI are most likely to progress to active TB? And basing on that, we developed research objectives, and they include a measure LTBI prevalence in percentage, the general population, and its subgroups, compare prevalence by subgroups, identify host factors, identify geographic clusters in LTBI prevalence, or LTBI incidence using the existing case notifications and constant contact screening data, and then correlate hotspots with socioeconomic and environmental factors. For the research contributions, I could say that we were able to estimate LTBI prevalence across Uganda, high-risk subpopulations, were able to identify major risk factors driving progression from latent to active TB. And then there was discovery of partial temporal patterns of latent TB transmission. We also cleaned and identified datasets of LTBI prevalence, surveys, and routine TB notifications. Like I had explained earlier, currently there are no valid LTBI datasets that are available based on to develop models. So we had to come up with something of our own. One of the research outputs, I would say that we developed a fully working model that could identify high-risk districts, and the model was an isolation forest. Well, we did model evaluation benchmark study. We deployed our system. We used the FAST API to integrate it. And then what we believe that we validated insights for public health. I believe that this is a very, very huge push in public health, and it's can be very useful in further studies. The methodology we used, as you can see in the diagram, we collected data and then we ingested it, then we processed it. We did EDA, exploratory data analysis, and then we did feature engineering, which was the features to use to train the model, and then we developed the model. We came up with 12 models, and among those 12 models, we came up with one model that performed really well, and it was an isolation forest. So to continue, after model development, we did model evaluation, and then prediction and risk scoring. This is really what we based on to determine what model to choose for production, our project. Then we did some visualizations, and then we developed a dashboard that would really display details and show how the Ministry of Health can allocate resources. For the dataset description, as you can see, we had TB notifications, and this is our provider, DHIS2/NLTP. And then we had to check the UBOS platform, and we were able to get population data. Mostly, we got most of our data from UBOS because it had a lot of census data, it had a lot of population data. And then also we got some data from WHO, and it's the one that really gave us insight on TB. And then we also got some reports from World Bank. Then also OpenStreetMap helped us to, map out get boundaries of the country. And then we also get some data from Ministry of Health. Ministry of Health mostly had reports, and we got a report from 2015, 2016, and that was a report talking about TB. Okay, now I'm going to pass on to my colleague, Farida, to take over and explain the remaining part. I remain Panamavin. Thank you.
Hello, I'm Farida Nachanzi, and I'm going to take you through the output results and the discussions. So here we have the feature distribution and density analysis, and it shows the distribution of the district level TB incidence cases. That shows a clear right skew, and the most districts are falling through the low or the moderate case counts. In conclusion, it's going to show that TB burden, and it's not evenly distributed across Uganda, and therefore we concluded that the simple mean-based analysis would not be effective, and hence we're going to apply the isolation forest. And then we have the feature correlation matrix. Here it shows that the population density and the TB case notification, they have a high positive correlation, and we notice that dense urban environments with inverse relationship to the socioeconomic index, revealing that the poorest districts may face barriers to diagnostic access. And then another idea is the box and whisker plot, whereby we have TB incidence cases against the administrative region, and we notice that the central region has high TB incidence, followed by the eastern, the northern, and then the western. And another idea is the log scatter plot, which is revealing that there is a dense cluster of the solid black points, revealing the normal and stable districts. Here we see that the blue is the central, and the green is the eastern, red is the northern, and purple is the western. These isolated peripheral points are the anomalies, and they're suitable for isolation, forest, and DB scan notification. And then we have the population pyramid, which is showing the population count against the age group. And we see that TB in Uganda is most dominant in the youth within 15 to the 24 age group. And then we have the TB program funding analysis, which shows that the 24-month funding projection reveals a persistent and widening funding shortfall in Uganda's TB program, meaning the actual funding starts below the optimal level and rises gradually, then it exceeds millions of dollars. The next one is the model selection and the deployment. Against the 3 group members, we were able to each create 4 models, and we evaluated only 7 of the different models, focusing on only the anomaly detection and the clustering. We realized that isolation forest stood out, and why it stood out was it had the best overall performance and a high precision. It also had the highest score. So why other models were not selected? It was because of the lower and complex weighted score. Spectral clustering showed a good structure, but it was weaker in detecting the performance. DP scan and HDB scan struggled due to sparse distribution. And here we have the model performance graph showing the different 7 models we talked about: the isolation forest, ensemble, spectral clustering, and KDA, Gaussian mixture, and the rest. And here is the summary of the model selection. Overall, it shows that isolation forest stood out, and it's the model you're going to deploy in our next steps.